Hi, I'm Travis and I'm an engineer on the academic team here at National Instruments. And today I want to show you a new approach to teaching PID in controls and mechatronics classes. As you know, PID is a popular control algorithm that most mechanical and electrical engineering students will be exposed to at some point in their academic career. However, PID is a mathematical algorithm commonly represented with diagrams on a chalkboard and computer simulations. But it's critical for engineering students to understand the theory behind a concept, and that's especially true of a math-heavy concept like PID. While derivations and simulations can act as a successful introduction to PID, many students are often left with little practical knowledge of how to use it. So let's go ahead and use some software that mimics what you might find yourself drawing on the chalkboard. In this case, I'm using Labview. So let's go ahead and open up that simulation. Now if I jump to the block diagram, you see that Labview is being used to implement a mathematical plant model so that we can tune our algorithm based on a representation of a real control plant. I can even choose from a wide variety of solvers, allowing students to learn the implication of each solver type. Now if I jump to the front panel again, I can run my simulation, and while it's running, I can have a choice of different gain inputs. It looks like that's throwing my system off. So let's go ahead and tune a little bit better. That looks pretty good. Now after we're satisfied with our gains in simulation, it's time to move to a real-world system. So I'm going to go ahead and stop this and exit out of this code. And we already see that on our embedded hardware, we have our code loaded up. So in this case, for our embedded hardware, we're using a myRio and the Quanser cube to represent one of our systems. So I'm going to go ahead and open up this exercise. And when I run it, we can see that our Quanser cube is representing the system that we're tuning with our mathematical functions. I'll go ahead and tune this guy. And it looks pretty good. I'm going to go ahead and stop that. Once students feel familiar with the basics of PID control, they can try their hand at a little bit more advanced plants. Here I have an inverted pendulum where we programmed a swing-up control on our Quanser cube. Let's go ahead and take a look. Now give it a little nudge to get it started. And once it's swung up, the control of the inverted pendulum is put into place. Now you've seen how using simulation software, students can simulate control algorithms and validate their assumptions before using real hardware. And when the time comes to move to physical implementation, students can easily transition their code to include real I/O. With this approach, students not only have the opportunity to learn foundational principles of PID, but also to see it in action, allowing them to not just conceptualize it, but experience it. To further explore this approach, download the free courseware link from this page.